So that is Boyle's law. So after Boyle's law, we have the Gay-Lussac's law. Let me give it a capital G since it's the dude's name. Shrink that a wee bit. And the Gay-Lussac's law says that if you take the initial pressure divided by the initial temperature, we will get the initial or a secondary pressure divided by a secondary temperature. So that is the Gay-Lussac's law. And let's see, we have Charles' law. And these laws should all formulas should always be available for use to you on any exam or quiz or anything. I don't find it useful to really memorize all of these. The only one that maybe you would memorize is the base one, which we'll go over in a moment. And from the base one, we could derive pretty much everything. But for your purposes, I would say that you should have access to the formula at all times. So Charles' law. Charles' law says that if we take the initial volume divided by the initial temperature, we will get the new volume divided by the new temperature. So what else do we got? We have Avogadro's law. Let me shrink this, try to fit this all in one line. We have Avogadro's law. And honestly, anytime you hear Avogadro, you should like immediately just think moles. And Avogadro says that we take the initial volume. Oh, what just happened? Something crashed graphically. You guys all see my screen and everything? Nothing, has anything changed? Have you lost any sort of visuals? All right, cool. My screen's black for a moment. So we have the volume divided by the number of moles equals the volume 2 divided by the number of moles. So pretty much these are our laws: the Avogadro, the Charles, the Gay-Lussac's, and the Boyle. And then we have a combined gas law. Or rather, not the combined, let's call this the ideal gas law. And that states that PV equals nRT. And let's say that R for our cases will be equivalent to 0.08206 liters multiplied by atmospheres divided by moles multiplied by temperature Kelvin. So these are all the formula that you pretty much have, and there's going to be a few more things that we have to pick up on, but these are the main formulas that we have to pretty much be familiar with. You don't have to memorize them, but we should be familiar with them, so in the sense that if we see them, we understand all the variables and how to plug the variables in, because really that's all that matters. P, V, T, N. So P is pressure, V is volume, T is temperature, and we have to note the temperature should be in Kelvin. Volume will typically be in liters, but we could use another unit. Pressure, well, pressure could be in anything, but if we're going to use this gas constant right here, we want pressure to be in atmospheres. But I want to say that you guys should not feel restricted to any specific unit, because if you're familiar with the units, you should be able to bounce between them. And if you're able to bounce between them, there's no real restriction on anything you need to use, as long as you have the ability to convert between. And N is moles, So pretty much anytime you see N in any chemical equation, it is almost always going to be moles. So pretty much this is everything you need to know for just about every sort of gas type question we will be going through. So let's look at our first question now. So we're probably going to have to, or I'm probably going to have to scroll up at some point to cut everything off. So it would be, I would say that you definitely should write this down somewhere if you're not familiar with the individual equations, just so you don't get lost as we go through. Some questions. No, let's call this problems. Let's say a 350 milliliter sample of oxygen gas has a pressure of 800 torr. Calculate the new pressure if the volume is increased to 700 milliliters. So this would be a type of question that you would be asked. Let's underline what is important. So we have a 350 milliliter sample, and we know that the sample has a pressure of 800 torr initially. We know that the pressure is going to go to a new pressure, so new pressure, and it says to calculate that new pressure if the volume is increased to 700 milliliters. So what we have here is a V, actually, let me change. So we have V1, and that's not what I wanted. We have V1 right here. We have a initial pressure right here of 800 torr, so that's our P1. We have a new pressure. It wants us to calculate this new pressure, and therefore this is P2. And it says the volume is increased to 700 milliliters. And so this will be our V2. So at this point, we have V1, P1, V2, and we need to calculate P2. Which equation do you think we should use to solve this? Yep, you are totally correct. We will use Boyle's law. So we will use Boyle's law. And that is also the correct answer. We would take P1, V1 equals P2, V2, which is Boyle's law. We know that we need to find this new pressure P2, so we need to solve for P2. That will become P1, V1 over V2 equals P2. And then we just need to plug in. So P1 is, let's see, 800 torr. We have a V1 of 350 milliliters. We're going to divide that. And then that is 700 milliliters for our V2. Notice how the milliliters cancel, leaving us with torr, which generates a value of 400 torr. So if we were asked a problem like this, this is how we would do about solving it. Let's do another one. Oh, any questions on that one, by the way? All right. Let's say a sample of nitrogen gas has a pressure of 300 millimeters mercury. At 200 Kelvin. Calculate the new pressure if the temperature is increased to 600 K. So let's look what we have here. Well, we have a sample of nitrogen that has a pressure of 300 millimeters of mercury. So we have some information right here. Let me actually decrease the thickness. That's way too thick. I'm using the wrong pen, I think. We have a temperature of 200 K. We need to calculate a new pressure if the temperature is increased to 600 K. So right here we have a T2. We have a new pressure, so this is a P2. We have an initial pressure, so that is a P1. And we have an initial temperature, so that is a T1. So which law do you think we will be using for this one? Yep. We'll be using the Gay-Lussac's law. And the Gay-Lussac's law states that the initial pressure divided by the initial temperature is equivalent to the final pressure divided by the final temperature. And we are looking for the final pressure. So all we need to do is multiply both sides by T2. This will give us the initial pressure multiplied by the final temperature divided by the initial temperature is going to give us the final pressure. And then after that, we simply plug in all of our variables, which gives us 300 millimeters of mercury multiplied by 600 Kelvin divided by 200 Kelvin. So after that, just punch that into our calculator and we will get a value of 900 millimeters of mercury. And we can leave it at that, or we can convert it if the question asks us to. And yeah, that should be good for here. Any questions on this one? Alrighty. Let us say calculate the new volume of a 250 milliliter sample of gas if the temperature is increased from 30 Celsius to 60 Celsius. So let us look what we have. We want to calculate. We want to calculate the new volume of a 250 milliliter sample if the temperature is increased from 30 degrees C to 60 degrees C. Well, let us check this out. We need to first recognize that the 30 degrees C is the T1 because we are going from 30 to 60, which means the 60 is the T2. Calculate the new volume. Well, this is a volume, obviously, and since it's the new volume, which means it is probably the final volume. So volume 2 of a 250 milliliter sample. So this is the volume 1. So we have all of our information here. Which law should we, oh, you already stated it, Charles' law. So we will use Charles' law for this one. Charles' law states that the volume 1 divided by temperature 1 equals the volume 2 divided by the temperature 2. Since we are looking for the volume 2, we simply need to multiply across by the temperature 2, which will yield us volume 1 multiplied by temperature 2 all over temperature 1 is equivalent to V2. I should also note that we are in Celsius here, so we want to do a conversion from 60C and 30C into Kelvin. So 30 degrees C. So we should always be in Kelvin for these equations unless otherwise stated. This will give us 333.15 Kelvin. This will give us 303.15 Kelvin. So this is all the information that we need to know to solve this problem. And let's just plug in all of our values. So we have 250 milliliters for our V1 multiplied by our temperature 2. And our temperature 2 is 60C, which means it's 333.15. So 333.15 Kelvin. We're then going to divide by our temperature 1, and our temperature 1 was 30C, which is 303.15 Kelvin. Punch that into the calculator, and we get, let's see, we should get 275 milliliters. Any questions on this one? All right. So a 200 milliliter balloon contains 0.25 moles of helium gas. What is the final volume of the balloon. If 0.75 moles of helium gas is added to it. So let's look. We have 200 milliliters. We have 0.25 moles. We have 0.75 moles. What else do we have? What is the final volume? So we have a V1, we have a V2, we have a V1, but this right here is not the V2. It says we are going to add 0.75. So we need to take the V1 plus what is added equals V2. So the V1 is 0.25. What was added was 0.75, which means we now have 1 total. So this is what V2 actually is. That makes sense, right? All right. So here's all of our information. What law will we be using here? Yep, Avogadro's. So Avogadro states that the initial volume over the initial number of moles is equivalent to the final volume divided by the final number of moles. We are looking for, oops, I put wrong subscript. There we go. So we are looking for V2. That turns into the initial volume multiplied by the final number of moles over the initial number of moles equivalent to the final volume. And let's just plug all of our numbers in. 200 milliliters multiplied by 1 mole divided by 0.25 moles equals 800 milliliters. So if we added 0.75 milliliter or moles of helium to a balloon that was 200 milliliters, it would increase to 800 milliliters. So that's how much it would go to. So let's see. I got a bunch more problems still. There's a bunch of different ways we could ask these pressure questions. So let's say we take a 400 milliliter sample of neon gas. That has a pressure of 2 atmosphere and a temperature of 300 K. Calculate the new pressure if the temperature increased to 900 K and the volume decreased to 200 milliliters. So let's see, what does this question want? We have a initial volume. So because it says a 400 milliliter sample of neon gas has a pressure of 2 atmospheres. So this is probably the initial pressure. At a temperature of 300 Kelvin. So we have a T1. Calculate the new pressure, P2, if the temperature increased to 900 Kelvin, so this is T2, and the volume decreased to 200 milliliters, and this is V2. So we have an interesting type of equation right here. We have a lot more variables than we normally have. What law will we be using here? I actually did not write it up on top. So we have one more, and it's called the combined gas law, and we talked about it. It was the first one we did. And the combined gas law is P1, V1, N1, T1 equals P2, V2, N2, T2. So let's take this. This is the law that we will be using. Blow this up a wee bit. I'll make this red. However, I want to make a note here. Notice how in this question, it does not ask about or tell us anything about the number of moles. So because of this, we could assume the moles stay constant, and therefore, we just cross them right out like we did before. And we get this new gas law that we just made up ourselves. P1, V1 equals T1 equals, I don't want to have that equals there, P2, V2, T2. So this is our new law that we will use. And like I said, we can always just go back to this original equation and we can manipulate it any way we want to solve for any sort of gas problem, really. So this is the combined gas law. So based on this information, we need to find P2, which is this guy right here. So let's solve for it. We will need to essentially multiply across by T2 and divide by V2, which will give us P1 V1 T2 divided by T1 V2 equals P2. So here is our new worked out equation. And at this point, all we need to do is just plug our variables into it. So let's do that. We have a pressure, an initial pressure of 2 atmosphere. We have a, let's see, we need a volume now. So we have an initial volume of 400 milliliters. We need our temperature 2, and our temperature 2 is 900 Kelvin. Now we just divide that by our temperature 1, which was 300 Kelvin, and multiply that by our volume 2, which was 200 milliliters. And when we punch that math out, we will get an answer that is 12 atmosphere. How about this problem? Any questions with this one? This one was a little bit longer, a little bit more work. All right. We will do one more of these pressure problems before we move on to something a little bit different. And then we will nearly be done with everything related to gases. So the next question will say 0.500 moles of neon gas is placed inside a 250 milliliter rigid container at 27 degrees Celsius. Calculate the pressure inside the container. Well, let's look what we have. We have 0.5 moles of neon gas is placed inside a 250 milliliter rigid container. When we see the term rigid container, that means that we are not going to have a volume change. The volume is not going to change. There will be no V2 at 27 degrees Celsius. So this is our initial temperature. Calculate the pressure inside the container. So based on this, we have an N1, we have a V1, we have a T1, and we have a pressure, which is our P2. Or rather, we'll just say our P. So, based on this, which equation or law should we use? Yep, this will use the ideal gas law, which is PV equals nRT. And in this equation, we are looking for P, so it becomes P equals nRT divided by V. We also need to know R, which is our ideal gas constant of 0.08206 liters, atmospheres, moles, kelvins. So we should note that our volume is in milliliters and our temperature is in Celsius. So we need to do a little bit of conversion here. So we have a temperature of, let's see, 27 C. We have a number of moles of 0.5. We have a volume of 250 milliliters. And what else? Let's see, we have, and that's everything. We need to convert this temperature to Kelvin, which is 300.15 Kelvin. And we need to convert this volume into liters, which is 0.250 liters. And moles are in the proper unit. Any questions so far on this problem? Or are we all on the same page? All right, excellent. So at this point, all we need to do is plug all of our values in. And so I will take the number of moles. We are going to multiply it by our ideal gas constant of 0.08206. And it is in the units of liters times atmospheres multiplied by or divided by moles of Kelvin. So make sure to always look at units, because that is how I know we need to be in Kelvin and we need to be in liters, because we need to cancel the units from this ideal gas constant. After that, we need to multiply it by our temperature, which is 300.15 Kelvin. And then that will all be divided by the volume of 0.250 liters. And we will see, I think it was blue I used. Moles cancel with moles. Let's see what else cancels. Liters cancel with liters. And what else? Temperature cancels with temperature, leaving us with atmospheres as our final unit. So when we punch all these numbers into our calculator, that's not what I wanted to use. I don't know why I keep mistakenly using it. We will get a value of 49.236 atmosphere. And we take significant figures into account, it's gonna come out to 50. Oh no, I'm wrong. Hold up. It's gonna come out to 49 atmosphere. Because we have two significant figures here. This actually should not be, it should be 0.25. Because this 0 is not significant and it's initially, we only have 2 sig figs. So we can't go from 2 sig figs to 3 sig figs. So it's 0.25 when we convert. Make sense? Are we all good on all these types of problems? All right. So we will now move on to the next topic, and this topic is known as partial pressure. And this is really simple. It really is. So what is partial pressure? So when we talk about partial pressures, we pretty much mean when we have multiple gases mixed together, what are the pressures that the individual gases exert? Everything we've been talking about so far has been pretty much one gas, and we have been looking at the combined pressure or the total pressure of that gas being exerting, the total pressure that that gas was exerting. And now we are going to look at mixtures of gases to determine pressure that the individual gases will exert. This is also known as Dalton's law. So the equation for this is the P total is the equivalent to the combined pressures of all of the other gases. So PA, PB, PC, etc. And that is literally it. We are going to take the pressure total is equivalent to the pressure of the mole fraction of the individual compounds. And what is the mole fraction? Well, PA is equivalent to XA multiplied by P So XA is what is known as our mole fraction. These values all right here are known as our partial pressures. So the partial pressures added together equivalent to total pressure, and each of the individual partial pressures are equivalent to the mole fraction of that compound multiplied by the total pressure of all the pressures. So the concept is really, really simple once we do an example. So let's say we have a chamber, and in this chamber we have nitrogen gas, we have oxygen gas, and we have argon gas. What we would say is the P total is equivalent to the pressure or the partial pressure of the nitrogen gas plus the partial pressure of the oxygen gas plus the partial pressure of the argon gas. And we would say that the XA plus XB plus XC, etc., will equal to 1. So when we take all the mole fractions together, they should be equivalent to 1. And that sort of makes sense because right here, the mole fraction is essentially going to be a ratio of all of the individual moles in the entire chamber. So we will say that we solve XA by taking the number of moles of A and dividing it by the total number of moles of everything in the chamber. And so we could also say that this is equivalent to NA divided by NA plus NB plus NC, etc. So we will take the number of moles total that we are talking about, and we will use that to find our mole fraction. Our mole fraction can then be essentially multiplied by our total pressure to define or determine our partial pressure. On top of this, if we add all of our mole fractions together, we should get 1. And that makes sense because the mole fraction is a ratio of all the moles that are inside the container. So if we add all the mole fractions together, they should equal 1 or 100%. Right. So let's say we have 2 moles of N2, 3 moles of O2, 5 moles of argon, and the P total equals 1,000 torr. So pretty much I have this chamber right here that I made. And it is at 1,000 torr. I want to know the partial pressures. So let's start this question off. We need to find the mole fraction of N2. We need to find the mole fraction of O2. And we need to find the mole fraction of argon. So this is the first step we need to do for these type of equations. So we know that we have 2 plus 3 plus 5, which equals 10 moles total. So we know that our total moles is 10. We know that we have the individual number of moles here for each of these as 2, 3, and 5. And so if we do that basic math, we get 0.2, 0.3, and 0.5. And you will see if we add all of these together, we get 1. Makes sense. At this point, all we need to do is take our mole fractions that we have here and multiply it by the total pressure of 1,000 torr, because this is how we essentially solve it. Because we take our mole fraction, we multiply it by the total pressure, we get the partial pressure. And so we will multiply each of these by 1,000 torr. And we will get the following values of 500 torr, 300 torr, and 200 torr. And as you see, if we add these up, 500 plus 300 plus 200, we get back to 1,000 torr. So all of our math works out, and we figured out the partial pressures that each of these gases are exerting inside this container. We have 2 more problems on here. So 2 more problems. Let's say I have 12 grams of helium and 4 grams of hydrogen. And we are going to place that in a rigid container. What are the mole fraction? What is the mole fraction of helium? So this is super simple. We first need to take these grams that we have and convert them into moles, because if we have mass in grams, we always want to go to moles. So actually, let me go to red pen. Take 12 grams of helium and 4 grams of hydrogen. We know that we have a molar mass of each of these. For 1 mole of He, we have 4 grams of He. And for 1 mole H2, we have 2 grams of H2. So now we have the moles. This gives us 3 moles of helium. And this gives us 2 moles of H2. And now we just need to figure out the mole fraction. So the mole fraction of helium is going to be, well, we're going to take 3, and we are going to divide it by 3 plus 2, or the 3 and the 2 moles, because we have those many in the container. And this will give us a value of 0.6. So we have a mole fraction for helium of 0.6 for our answer. Any questions on this one? All right, so I have one more question on partial pressures. And so the total pressure of a sample containing N2, O2, and argon is 840 torr. The partial pressure of N2 and O2 is 600 torr and 160 torr, respectively. Calculate the partial pressure and mole fraction of argon. So this is a little bit more involved of a question. We need to do a little bit more work, but it is mostly solvable with a few simple steps. So what do we know? We know that the partial, geez, I keep clicking the wrong pen. We know that the partial pressure of oxygen is 160 torr. We know that the partial pressure of nitrogen is 600 torr. 60 torr, 600 torr. And we know that the P tote is 840 torr. We need to know the partial pressure of argon. And we need to know the mole fraction of argon. So, based on this information, how do you think we should go about solving this problem? So how are we going to get the pressure for argon? Well, we have P total, and we know that the P total is equivalent to all the pressures. So we will say that 840 torr is equivalent to 600 torr plus 160 torr plus the partial pressure of argon, because we have the partial pressure of nitrogen here, and we have the partial pressure of oxygen over here. And so, yes, we get the partial pressure of argon with a little bit of math equivalent to 80. So how about for the partial pressure of argon? How will we do that? We know that the partial pressure of argon is equivalent to P total, or not the partial pressure, the mole fraction rather. P total multiplied by the, where are we? Oops, a little bit of a mistake here. We know that P total, oh geez, what's going on with the pen? P total multiplied by the mole fraction is equivalent to the partial pressure. And so if we have that, we could say that the, let's just write it below. We have that the mole fraction of argon is equivalent to the partial pressure of argon divided by the total pressure. And so we just need to plug our values in, which is 80 divided by 840, and that gives us 0.0952. And because we only have one significant figure here, it should round out to 0.1. Make sense? You guys all feel confident on these types of equations? All right, awesome. This will be the last thing that we talk about. And this is diffusion versus effusion. So when we are talking about diffusion, We are talking about a gas moving from one area to another. So the gas is essentially passing through a very wide opening, and it is diffusing into the other gas in the surrounding area. This is how we pretty much describe diffusion. Any sort of diffusion is essentially a gas being diffused or spreading throughout an area of another gas. That is all diffusion is defined as for your purposes. So we'll call this diffusion. Now, effusion is a little different. Effusion is, let's draw a box again. I actually use shapes. And we'll say that that is a tiny pinhole. We're going to have particles in here again of gas. And they are going to go through that pinhole into an empty chamber. This is known as effusion. And this is pretty much measuring the rate at which gas particles will evacuate a chamber through a tiny hole. And the reason we have to differentiate the two is in the first one, the gas particles are not being restricted in any way. They're free to essentially fly out and interact with other gas particles. While in the case of effusion, the gas particles, although they can evacuate out the hole, you have to realize the gas particles are nothing more than individual molecules that are bouncing and flying around. So in order for gas to evacuate this hole, all the gas particles have to bounce around and then hit perfectly through that hole to exit that hole. So the rate at which the individual particles will leave that hole can actually be measured. And it is actually a function of their temperature and a function of the mass. So pretty much at a certain temperature, we are going to have a certain rate. So the equation for this is rate 2 divided by rate 1 equals the square root of the mass 1 divided by the mass 2. That's the equation. So let's ask an effusion question. So the rate of effusion of oxygen. So let's say that R1 equals 0.20 moles per minute. Calculate R1 or R2. This would be all the information you'd essentially be given. Actually, I made one mistake here. Let's say R equals rate and M equals molar mass, not not mass, molar mass. So in order to solve an equation like this, these equations are incredibly simple. You literally just plug in the values you're given and solve. So we have R1, so we would say 0.2 divided by, and R2 is going to go on top, is equivalent to, well, the molar mass of oxygen, or O2, is going to be 32. And the molar mass of, let's see, the molar mass of the, let's say R2 is, R1 is oxygen, R2, which is going to be helium. So we're comparing oxygen and helium here. So helium has a mass of 4. So here is the setup for our whole equation, and at this point we are just going to solve for R2. So punch this into our calculators and we get R2 equals 0.5657 moles per minute. So these is essentially how you do these effusion problems. Very, very, very simple and straightforward. You'll be given one rate and you will be asked to decide or determine the rate of something else. And that's really all there is to a problem like that. Any questions on this? Any questions on anything that we've talked about today or yesterday at all? Because if not, that is pretty much all that I really want to talk about in regards to gases. And so that'll pretty much be all we talk about for today.